Hi, and welcome to the Deep Embedded channel. If you are a software engineer like me, and you still want to be able to do cool projects on FPGA, like that one, a divider, keep watching. Okay, so hello everybody, I'm Ari, and I am not an FPGA engineer. Okay, that's very important because I want to show you that it can be a great hobby and a great area to develop to. Okay, so I'm a firmware engineer in my profession, and I'm not an FPGA professional. Okay. So some prerequisites, some basic university stuff, I would say, like gates and flip-flops and MOOCs and the MOOCs. And when we really need it, I'll try to elaborate just in case somebody has forgotten any of it. Okay, so what is an FPGA? So this is a picture from the board here. I'll show it shortly. That's a chip with flexible functionality. Okay, it can be whatever you want it to be if you know to program it. And contrast that with a chip like AVR. This is an Arduino. So AVR knows to be only an AVR. Okay, so that's an ASIC, the application-specific integrated circuit, and an FPGA is flexible. Where do we use FPGAs? So back in the days, I would say maybe 10 or 15 years ago, somebody told me that he knows of places where FPGA goes because those are big companies with very expensive products, so they can afford to put FPGAs in the products. So like high-end systems, like super expensive routers, you could see FPGAs. And in press silicon work, for example, companies that produce their own hardware and they want to start working in parallel developing firmware, so they could take the model, put it on FPGA and start working early instead of waiting for the ASIC to be ready, which takes much more time and you have to work one stage after the other instead of parallel. But today you can find FPGAs almost everywhere, and you have FPGAs starting from just several dollars up to tens or hundreds of thousands of dollars. You have the entire range. Okay, there are several types. There are very, very primitive types, not of FPGAs, but programmable logic. Back to the 1960s, then we had the PLA, and it's even between the PAL, but I don't think any of them are used anymore. The two types that are still being used is the CPLD, which is a complex programmable logic device, and it's like the simple brother of the FPGA, which is the most modern way to do programmable logic. But it's still used. I actually have a shipment of a rather new board on its way that is using a CPLD, and this board here is using an FPGA. Okay, the market leaders are Altera, Intel bought Altera, and Xilinx. In 2016, they dominated about 90% of the market. There are smaller companies as well. I mentioned Lattice here because I've noticed they have some very interesting direction of having their tools open source. I didn't yet explore that. I don't know how well it goes, but it's a very nice direction because the bigger companies, Xilinx and Intel, they will give you their tools with restrictions. So I will be showing here stuff with the Intel software. I think they have a limitation of maybe 10,000 lines and other limitations as well. Okay, so you may ask yourself, why do I need that? Is there anything that I cannot just do with an MCU like AVR on an Arduino or something like that? So something that you can do is to do hardware offloads. Okay, if you have, let's say on the same board, you have a primitive MCU like AVR, and you have an FPGA, you can supplement the functionality of the AVR with adding logic into the FPGA, and they talk with each other, and you can enhance things. I gave one example here, it's vector math. Okay, if you do vector math in something that doesn't have vector math support, then you have to do it the hard way. If you can supplement with extra hardware, it can be much faster. Of course, you have some overhead of moving the data from one to another. You have to consider if it's worth it. Okay, learning. If you want to understand better how hardware works, you can actually build some, not every hardware you can do in FPGA, but many of them you can, and you can actually build one, connect it to shelf products and see that everything works together. It's pretty nice. Speed-hungry applications. Sometimes when you have high frequencies, you need stuff to be done really quickly. MCU doesn't cut it. You have to use an FPGA because generally for a given number of cycles, an FPGA will be able to do more because it does exactly the tailored task that you have designed it to do. While an MCU is a general purpose computer, so it will take longer on an MCU. Okay, you can prevent board redesigns. Okay, if today everybody can design small board. If you put an FPGA on it, then potentially in the future you want to add a little bit of digital hardware. You can do that by just changing the content of the FPGA, instead of potentially redesigning the board with the new hardware. And of course, it's just super cool because it's hardware performing tasks. For me, it's sufficient to go explore it. Okay, and several maker products in the market. So this is the DE0. It's being produced by a company called Terasic. And this is the FPGA right here. And it's a Cyclone 3 by Altera Intel. This is an Arduino NKR Vidor 4000. I have no idea why they gave it this name, but it has an Intel FPGA here, and it has a microchip ARM processor here, and they can talk with each other and do all kinds of stuff. It has a PCI extension and tons of stuff. And there is also Tiny FPGA. I didn't have a royalty-free picture, but for a few dollars, I think maybe starting by about $15, you get a little board with, it's based on Lattice FPGAs, and they have larger boards, so there's plenty of what to work with. Okay, and generally, in recent years, FPGAs are being democratized in a similar way to how Arduino democratized MCUs. Okay, so this was an introduction, and let's get a little bit more technical about how it works. Okay, so maybe you ask yourself, how is it possible that we have something like hardware that is hard by definition, but still we can change what it does in the field? Initially, it can look a little bit contradictory. So if we take two truth tables, and generally digital logic is a bunch of truth tables chained together. So we have two functions here, which is AC plus B, or not A plus BC. And I want them both to be implemented with the same hardware. So one way would be to do something like that. For every entry, I have the entry and its negation. Everything is connected to everything. And I have sum of products right here. And those connections, I didn't draw arrows to all the connections, but you get the point. The connections are being dominated controlled by flow gate transistors. So essentially, you can close and open each of those junctions. So if I wire only those junctions and open the rest, I get a not A or BC. If I do this, I get an AC or B. Okay, so that's one way to do that. I think it's more typical of CPLDs. And if you connect a flip-flop at the end, then you have a more-whole logic unit that it becomes more interesting to do something like that. And you have many of those connected together, and you can start implementing logic this way. Okay, let's look at a more modern way to do that that is more typical to FPGAs. Okay, we have our truth tables back. And our friend, the mux. Okay, if you don't remember what the mux is, you have two inputs, one output, and a select input that will, if you set it to 0, then the 0 input will go out through the output. If you set it to 1, then the 1 input will go through the output. Okay? And I built something like that. The green layer I will be used to assign inputs to the legs of the leftmost muxes. And my inputs, my real inputs, which is A, B, and C, are going to control the muxes. And A is controlling the entire leftmost line or column. And the same for B, and C has only one. C is controlling that one. And now I want to assign inputs properly on the green field, so it will implement my truth table. Okay, I want to do AC plus B. Okay, so first, if B is 1, I get a 1, right? So I put 1s there, and if B is 1, no matter what A is, no matter what C is, I will get a 1. Okay? See that? Okay, now I go to the other direction where B is now 0. Okay, I took care of B equals 1. B is now 0. I want a 1 only if both C and A are 1. Okay? So here I put C, I want C to be a 0 and get a 0. Okay, so I've assigned both entries here to 0, and this is a mistake right here. Forget it, it should wait to the next phase. Okay, and then if A is 0, sorry, this is A1 actually. So if C is 1, A is 1, I get a 1, A is 0, I get a 0. Okay, so I've implemented AC plus B. Okay? And this is not A plus BC, same hardware. I just changed the programming field. Okay, and a real logic unit will typically have a few LUTs. What I just showed you is called an LUT that's a lookup table. It will typically have more than one, plus a flip-flop and additional logic. It can be way more complex than that, and they try to mix it such that it will be powerful and not wasteful at the same time. Okay? So memory cells hold the programming at the green field. Okay, this is how I determine what the FPGA is going to do. And I have to somehow populate those fields because they are volatile. So I have two ways. First of all, I will keep my programming in a non-volatile memory. It can be flash, it can be EEPROM, whatever. Somehow, when I power up the FPGA, it has to move to the volatile cells. It can be SRAM, for example, holding those programmings. So one way, which is called passive, is in which FPGA is part of a big system, and some other part of the system is tasked with loading, making the loading into the FPGA, and only from that point on, the FPGA becomes functional. Okay, and there is an active way in which the FPGA has what it takes to load itself, in a sense, okay, from the non-volatile memory into the volatile memory. Okay, so we touched a little bit, 30,000 feet of how they work, and let's see how they are programmed. Okay, so we use HDLs, hardware description languages. VHDL is a pretty old one, but I think it's still popular. And Verilog and System Verilog, I think, dominate today. System Verilog is a variant of Verilog, in which they have added some constructs based on learnings that can prevent some mistakes. They've also extended how the language can help you with testing. So it's a more complete language, but I think Verilog is still being used a lot. Something that is super important to understand about working not just with FPGAs. Right now I'm talking about digital design. Later on we will apply to FPGAs. But any digital design, whether it goes to FPGAs or ASIC, you have to switch. You are moving to full concurrency, not the concurrency you know from processors. If you have one core in a processor, you're not really concurrent. You're just switching from one test to another. Here you can do things really at the same time, and you have to switch to that kind of mindset. And you have new challenges that will be new to you if you are a software engineer. Syntheses, I'll get shortly to what that is, and issues of timing. Let's start with timing. I didn't go very deep here, both because I think it would just inflate the talk, and I'm not an expert, but just in high level, we are dealing with physical entities. Physical entities have delays. Electricity doesn't move in an infinite speed. It has some speed, some finite speed that it moves through the elements. So if you have less elements on one port than the other, you can experience the result coming out as different delays on the ports. So that can cause two issues. One of them is glitches, which means that 4 times the output is not what it should be, but glitches, basically you sort out with flip-flops that sample at certain times. They sample the output, and it kind of, if you do it right, they kind of irons out the problems. A bigger problem that exists is metastability. Okay, and it means that in high level, if you have a flip-flop and we're looking at the clock, just the time just before the clock rise and just after the clock rise, throughout this entire time, the input to the flip-flop have to be held stable. And if it's not stable, it means that the flip-flop may sample some unknown value. And this is a much bigger problem because this unknown value can then propagate through the system. And for example, if you have a state machine somewhere, it can spiral out of control because you did not design the state machine to hold those unknown values. You have no idea how that's going to end up. And the only way out of it may be to just restart the system. So that's a bigger problem. And there are tons of tools that digital designers work with in order to analyze their code and try to surface all those problems. And you may find yourself changing your design, like adding flops because some paths may be too long for the propagation to be quick enough. So you need to cut it in the middle with a flop. There's a big deal around it, okay? But that's I can't go any deeper about that. But just bear in mind, it's something that exists. If you're a hobbyist and your designs are very small, the chances are that you will see less of those. The larger you get and the quicker you get with the clock, you will get more problems like that. Okay, so when we write, okay, we will do things in System Verilog here. When we write System Verilog code, it's going to be compiled similar to normal code, like interpretation of just understanding what the code is. And then, not an interpreter, just understanding what the code is. Then we're going to synthesize. Okay, so synthesis is, we want to move from the stage in which we have code, we need the real hardware to be produced out of the code. And there is something here that is very different than software. In software, you don't usually have to deal too much with the resulting binary. You just want it to work. Unless, of course, you have very special optimizations, then, okay, you need to play with it a little bit. Here, you can write code that will compile, it will pass simulation, but it can't be synthesized to real hardware. You did something there that just, the synthesis tool just don't know what to do with it, and it will just throw an error. Okay, I can think of one example is you can actually write a for loop. Now think what for loop means in hardware. A for loop, for example, can be a huge cascade of elements, one after the other. It will not just automatically translate into having flops and doing them in a for loop. It's not going to happen. You can use for loops even in synthesizable code, but you have to know very well what you're doing. Okay, it will not just always work. And the last part is place and route. Here in the FPGA, it's just automatic. I mean, with this software suite. But you still need to think about synthesis. And if I have time, I'll show you an example of what happens when you don't think about synthesis. Okay? So one tip that I have from the pros is to always start your design by envisioning the resulting hardware. Okay? Not just a good design. That's not what I mean. Not just designing it well. You have to think about what hardware is going to come out of your design. Okay, so let's take an example of this. Okay, I thought what would be interesting and simple at the same time. Okay, for people. So divider. Okay, if we take AVR as an example, it doesn't have a divide instruction. Okay, so I'm going to show a very, very simple divider. It's going to be very primitive. Okay, this is the box that I want to build. Okay, I have two numbers u and v, and I want to divide u by v. Okay, I also have a reset. Okay, and the reset line is going to just hard reset. It's asynchronous reset. It's going to reset the entire thing. And usually, what happens is that this is going to be part of the system, and there is a reset line throughout the system, and the entire system is going to go to reset. And I have to respond to that. I'm going to have a load line, okay? Because I don't want to continuously sample those. I want to be given a command, okay? Load now and consume UNV. Okay, consume UNV, make your calculation, and next time I do a load, then reload a different set of values. Okay, you don't want to continuously load. Okay, and I want the remainder and the quotient to come out after a number of cycles. Okay? So I'm going to use a super primitive algorithm, non-efficient but simple. Okay, I'm just going to do subtraction until I'm done, basically. I do subtraction time and time again. I'm going to count how many subtractions I needed. And that's going to be my div, and my mod is going to be what's left in U. Okay, I'm subtracting v from U again and again and again. So I'm starting to envision how the hardware is going to look. So I'm starting simple. First of all, I want to sample v. I cannot just use v throughout the computation. I need to sample it at the beginning, so changes here will not interfere with the rest of my calculation. So I have a flip-flop here, and of course it's a bus, okay? I put one flip-flop here, but it's a series of flip-flops because v is actually a multi-bit number, it's not just one bit. Okay, so it's a bus, it's called the bus. So I have a series of flip-flops, but you'll see in the code, I don't have to do something special in order to get a bus of flip-flops. It's coming free. Okay, and I have a mux here, and depending on load, I can decide if I want to consume v or just keep my current value. Okay? Okay. So this is the code that will do that. So there is an always expression. Okay, there is a sensitivity list here. And I'm saying always, and this is a system variable, always FF. I'm already telling him this is a flip-flop. Okay? Whenever there is a pause edge of the clock, or a negative edge of the reset, and reset is active low, so I'm calling it reset B, which is bar, reset bar. Then, okay, if I'm being reset, then reset, okay, just put a 0 in there. Else, if we're loading, then make a copy, and what happens else? Nothing, I'm just retaining my value, it's implicit, okay? By the way, not a great way to write code, okay? I don't do any begins and ends and stuff like that because I want it to be small, fit into the presentation. Not necessarily recommended. Okay, now I'm going to handle the current queue and I'm going to connect that to a comparator. Okay, because I want to stop whenever current Q goes below V or current V. And this is my counter. Okay, so first of all, this mux is being controlled by the result of the comparator. I have a counter, and I'm adding either 1 or 0, depending whether I'm stopped or not. Until I'm stopped, I'm going to add 1. Once I've reached my result, I'll start adding zeros or just keeping my current value. So this is the code for the mux. Okay, I actually call it the adder mux. And this will cause to add ones as long as this condition is met. Otherwise, it will start feeding the ALU with zeros. Okay. This is the code for the counter flip-flop. Okay, again, reset, I reset. And unless, okay, if I'm loading, I'm putting a 0. If I'm not loading, I'm just progressing it by the mux. Now you may ask, why do I need? I'm actually zeroing the counter at 2 places. Okay, one is here, and one is here. Why do I do that? That's because you have to separate. There is an asynchronous reset and a synchronous reset. So, and you don't want to mix. I don't want my design, because between 2 numbers, what do I do between 2 numbers? I have to zero the counter. I don't want to use the reset signal to zero my counter. That's a brute force thing that I don't want to do. Okay, as long as the system is not in reset, I want to do it in a sense gracefully. So I do it synchronously. Okay, I just put a 0 in there when the load signal is up. Okay, and last is the current Q. Sorry. So most of the time I'm subtracting. Yeah, that's by the way, that's a mistake. I'm not subtracting ones. I'm subtracting these. Sorry about that. Okay, I'm subtracting these. So a line should come here. And again, this logic controls if I'm stopped or not. And last, okay, this is the code for the U flip-flop. Again, on reset, I reset. On load, I consume U. And the rest of the time, I'm doing subtractions. Okay? And my output, most of the time I output a 0. When I'm ready with my result, I will output the result. Okay? And current U will come out as my mod, and the counter will come out as my div. Okay? And this is as simple as doing that. That looks like C. Okay? Any questions? You either understand everything or don't understand anything. It's fine? Okay. So we will do a live demo. Usually it's a very bad idea to do a live demo without a backup video, but I don't have a backup video, so I hope it will just work. So this is my FPGA. Okay, I'm going to load the FPGA with that program. Okay. When I just start the FPGA, this is an FPGA board. The FPGA is just the chip here. Okay. Okay, I'll start the FPGA, and this is what happens. Okay, it have loaded this program that is doing that. It has loaded it from the non-volatile memory, and there is a switch here. When I burn it, it's either I burn it softly. I'm just changing the SRAM, which means that when I shut that down, my programming will vanish. I can switch to a permanent flashing, which means it will flash the non-volatile memory here, whether it's flash or EEPROM, I don't even know. Which means that starting that moment, when I start it, my design will be the one loaded, okay? But I don't do that generally because NVMs have a finite number of burns. You don't want to ruin it, and you don't really have a reason. Most of the time, this is a dev board. You're not going to deploy it anywhere, so not much incentive to burn the flash. Okay, so I'll restart that. So what I want to do first, when I approached this board, is I have no aspirations to just throw my code at it and expect that it would work. Okay, so what I did at first is define a module with an output, I call it LED, and then assign LED with 1. Okay. This is already compiled. I wanted to save a minute, but I'll have to recompile very soon. So I go to the pin planner. Okay, the pin planner, you can already see that I've assigned, okay, ignore switch, okay, it doesn't exist in the module. It will exist in a second, but right now it doesn't. You can see LED. LED is assigned with pin J1, which I just took from the pretty good board documentation. So J1 is LED G1. Okay, so this means the FPGA, of course, does not know what is connected around it. So I'm telling now the FPGA how to connect a specific pin to my module. Okay, so the pin on my module, LED, now goes into the LED. Okay, I'm going to delete that. Okay, now I have to recompile because I changed the pin assignment. Now you can see, by the way, all the steps that I talked about, like analysis and synthesis, and after that there is time quest. Time quest is when you do have timing issues, your design justifies it, you will have timing issues. It will help you identify them. Okay, now I open the programmer and I do a start. Okay, and you can see that the rightmost LED is on. Okay, so what I did then, I did that. Okay, sorry. Okay, I just wanted to know that it works the way I think it works. Okay, that's it. I just connected switch to the LED. Okay, I'm going to recompile that. So, okay, I have to recompile it first so it knows switch. Okay, I guess there is a better way to do that and not go through the entire build process, but I don't know yet what that is, so I just compile, okay, and then I go to the pin assignment, pin planner, and now I have switch here, and I remember it's pin J6. Let's just make sure. Okay, so J6 is switch 0. Now you can see all the question marks. I have to recompile. It has identified that I have changed something. Okay. Okay, burning. Okay, on and off. Okay, on, off, on, off. Okay. Okay, that was enough for me as a sanity check. So that's my program. Okay, that's the program I showed you before, almost as is. Okay, I have defined the inputs and the outputs of the module. Okay, and here's the code. I've already shown you that's code in pieces. That's the code. Okay, there's nothing to it that is more than that. This is my divider module. In order to present it nicely on the 7 segments, I needed another module. Okay, this module is BCD to 7 segments, and it receives 4 bits nibble and outputs a 7 bits encoding for the 7 segments device. Okay, and as you can see, it's just a K-switch. For every numeric value, a 1 is off and a 0 is on. So for 0, I have everything in 0 is on except the middle one. Okay? I see question marks. Okay, I have 7 segments devices here, and I want the result of the division to be presented on the devices. Okay? So they have a specific, each segment here. If you put, it's active low, okay, you put a 0, it lights up. You put a 1, it turns down, turns off, okay? So this is this module. And this is what is called the top module. The top of my design, and everything is like under the top. So what I have here is that I have one instance. You can think of it as my module is like a class. So I have one instance of my divider, and I just connected everything. My input is going, I have only 10 switches there, so I only have 5 switches per number. So this is how I concatenated. My U is going to be 5 bits. I added 3 zeros, and the same for V. Okay, I just don't have enough switches on that board to do 8 and 8. Okay, and then I created instances of the 7 segments, and I have connected them to those outputs, which I will shortly connect to the right pins. Okay? This is the dot. I want the dot lit. Okay? So I created a port for the dot. I just assigned it with a 0. A 0 means it will be, the light will be on. And then I have a small piece of code here, because you remember I need the load signal to come up once in a while. Right? So I decided I'm going to wait 400 cycles, and every 400 cycles, first of all, I have a counter here, and I will zero the counter, otherwise I will progress the counter, but whenever the counter is 0, I will put load to 1, otherwise I will put load to 0. So I will have exactly 1 period of the clock with load as 1. Okay? Okay. Now, since this is not a one-liner, this is another very important tool, which is the simulator. You cannot expect your design, even a simple one, to just work. Okay? First you go, you do simulation. This is much easier to debug. Okay, now what I did here is that both programs are looking at the same code. Okay? But these programs add what is called a test bench. So this is my test bench. Okay? Forget about the simulator, the FPGA for a second. Now we are in the simulation world. Okay? This is highly non-synthesizable code. Okay? But the purpose here is to stimulate my real code and see how it works. Okay? So there is an always clause here. This is the clock. This is how I simulate the clock. I tell it every 10 nanoseconds, toggle. This will give me a clock. Okay? With a period of 20 nanoseconds. Okay? It's toggle and then I toggle again, so 20. Okay? Now I init everything. This is an initial block. You cannot do an initial block in the real hardware. Only in a test bench. Okay? I zero everything, then I wait for 10 nanoseconds. I wait for the next positive edge. I cancel the reset. I do a load. I wait again. Load is 0. Then I wait for 1,000 cycles. 1,000 nanoseconds, and I test a different set of numbers. Okay. I'll compile it all. Okay, this is what it took to compile it. And then I'll run simulation. I'm taking my signals from the test bench, and then I will run, you can see here, for 2 microseconds. And I will take those signals and I will make them pretty by changing the radix to unsigned. Okay, so that was the simulation. You can see here, okay, we begin in the reset phase, and quickly we do a load. Okay, the reset is cancelled here, and we do a load. You can see my U and V are decimal 255 and 7. And after a number of cycles, you can see the result, okay, being outputted on the output lines. Okay? And of course, the number of cycles that it will take in this primitive, I mean, even in better algorithms, it depends on what numbers you're using. Right? If you are dividing a very large number by a very small number, you'll get more cycles. Okay, what I'll do now is I'll skip to the next load. Okay, here I'm loading 255 states. I've changed that to 100. That's a very quick calculation. I have very short number of cycles, and I get, okay, 2 and remainder of 55. Okay, so my simulation, let's say that this is enough and it works. I go to the Quartus program, and this is already compiled. You know what? I'll compile it just in case. And I've already done the pin assignments. There are plenty of them. Okay, so I've prepared them in advance. Okay, if we look at the pin planner, you can see here all the pin assignments, okay, of the switches, of the 7 segments, of the clock. Okay, the clock, there is a clock on this board. I had to connect it into a 50 megahertz clock, and the dot. Okay, I will burn that. Okay. So, first of all, you may ask yourself what happens in division by 0. What happens here is that you get a 0. Okay, that's the definition for this implementation. Divide by 0, you get a 0. I don't have anything that is much smarter to do for this implementation. Okay, I have 5 switches. Okay. This is 1 divided by 1. Okay, this is not a decimal dot. Okay, that's just a separator. So I have 1 with remainder of 0. Let's do, this is 9 divided by 1, so it's 9, but 9 divided by 3 is 3. Okay? 9 divided by 7, okay, 1 with a remainder of 2. Okay, what's happening here is that it's running all the time. It's sampling my switches all the time. 1 in 400 cycles, it will do a load and compute the results. So it's happening millions of times. You don't see that, but it works. Okay? To conclude that, let me show you something nice about synthesis. If I go here, and remember the 2 programs are looking at the same hello SV file, and I actually accidentally, what I did was to do that. Here, in this always clause, instead of zeroing my V flip-flop, I accidentally tried to zero my current U flip-flop, like here. Okay, I did too much copy-pasting. Now I go to the simulator. I go to the project. You can see that question mark means I changed the file. I do a compile all. It compiles fine. Okay, it compiles fine. In a second you will see there is a V mark. It compiles perfectly fine. Then I will go to the library and I'll rerun the simulation with this new code. Okay. I'll do everything just like before. And I run and everything is fine. Everything is fine. And the reason that it is fine is because it doesn't really matter functionally. Okay? It doesn't really matter functionally if I do that here. Okay, because I will be loading a value here anyway. Okay, so it just worked. Okay? It just worked. But what happens when I try to build it in the quarters that includes syntheses? Okay, it fails. Okay, it fails. Okay, it's saying that I have multiple drivers on current U. Okay, I've tried to connect two drivers to the same port, so it just can't work. So it's a very easy example of how you can cause synthesis problem, even though actually it kind of worked in simulation, but it just can't synthesize. Okay, but this is a very naive, this is a mistake. Okay, you can do what you can think of as valid code, and it will not synthesize. You need to really take care of writing synthesizable code, and there are tips, from the pros, like they have their methods how to do that. But I kind of gave you, I think I kind of gave you the biggest one. If you start from envisioning the outcome, how the hardware will look, and then you derive the code from that, you significantly reduce the chance that you will end up with a non-synthesizable code. Okay, so that's it. Any questions? Everybody is in shock. אוקיי?
אני אשאל בעברית, למה בתוכנה שכתבת שתרוץ על ה-FPGA לא דאגת להעלות את הקלוק? זה משהו שהחומרה עצמה דואגת לך? ואם כן, אז מה המעורבות?
So the question is why I did not cause the clock the same way I did in simulation. Why didn't I create the clock same way I did in simulation? And the answer is I can't. Okay, without any external signal that will tell me that time progresses, I cannot bootstrap myself into that. Okay, think what logic would I do? How do I know that time has passed? I don't. Okay, so usually you have a crystal, external crystal that pulses in a certain frequency. And usually you use a PLL, which kinds of, it makes the signal in a higher quality. Here I think, maybe I just used the crystal, I think I used the crystal itself here without the PLL. Okay? Any other questions? Thanks. All right, I hope you have enjoyed the talk. This is 16 divided by 2. Soon I'll upload the code to GitHub. Feel free to take a look. Also, if you have any questions, please feel free to leave them in the comments section below. And also to subscribe to this channel to get updates whenever I upload new content. Bye.